So here we've got a gravitation question from Further Mechanics 2 in the dynamics topic. And this is what the question is, and essentially it's basically a particle being fired upwards from the surface of the Earth. And you've been given some conditions, and the gravitational force is k over x squared. When you're on the surface of the Earth, the acceleration due to gravity is g, and the Earth is modeled of a sphere with the radius r. So to start off the question, you have to show that k is equal to mg r squared. And to do this, all you have to know is that by Newton's second law, the total force is equal to the mass times acceleration. And we know that the force is k over x squared, and this is equal to mass times acceleration by Newton's second law. But we also have one additional piece of information that we've been given, and it's this bit. At the surface of the Earth, the acceleration due to gravity is g. If I rewrote that in mathematical form, what it's essentially saying is that when x is equal to r, a is equal to g. So therefore I can rewrite it by saying k over r squared is equal to mg. And if I just take r squared to the other side, or multiply both sides by r squared essentially, I get k is equal to mg r squared. And that would be enough to secure the 2 marks for part A. So now for part B, which is a bit more complicated. We've been told when it's at a height r over 4, so that's basically x, above the surface of the Earth, the speed is this, root gr over 2. And so that's our velocity. Now you want to find in terms of r, the greatest distance from the center of the Earth. So now what I'd like to do is I'll just take a minute to understand what the question's asking. When it's telling us to find the greatest distance, track your minds back to A-level maths like projectile motion. When you've got a projectile being launched from here, for example, like this, at this point where it's at its maximum height, the vertical component of the velocity is 0. And that's essentially what's happening here. To find the greatest distance is when the velocity is 0. So now what I can do is I can say, so if I just start off with a quick diagram first of all, just show taking upwards as positive. Ooh, that's not positive. Upwards is positive, and this is our object or particle P. It's got gravitational force acting downwards of k over x squared, and so that's negative. So now I can write that the total force sigma F is is ma. So therefore ma is equal to negative, because it's downwards, k over x squared, and we know k is mgr squared. So negative mgr squared over x squared. So before I continue, I'd just like to reiterate why there's a negative sign here and why it's so important. It's because it's acting, we've been told over here, the gravitational force is directed towards the center of the Earth, and we've defined the upwards to be positive. If I did the opposite, if I said downwards is positive, the negative sign, if I said downwards positive, this negative sign would just be over here. It's the same thing. One just needs to be negative because of the direction of the gravitational force. So now I can cancel out the m's. Let's just start by doing that. And now I've got a is equal to negative gr squared over x squared. Right. We want to find r, and we've been given the speed. So we want to find the displacement, we've been given speed. And in to do this, what we need to do is we need to redefine what acceleration means. So let me just take this step by step. Acceleration is the first derivative of velocity, which is equal to dv by dt. Now, if I use the chain rule and I just rewrite dv by dt, I can say that dv by dt is equal to dv by dx multiplied by dx by dt. And this is just velocity. The first derivative of displacement is just velocity. Therefore, I can just say acceleration is v dv by dx. That's a v. And so what I do right now is I just rewrite it by saying v dv dx is equal to negative g r squared over x squared. Technically, this topic is it's more focused with chapter 4 as opposed to chapter 5, but it still works. So now it's just a bit of separating the variables, A-level maths. Let's take dx to the other side. So we got v dv is equal to negative gr squared. So I'm just going to take out gr squared. Why? Because it's constant. G is just the acceleration due to gravity, so 9.81. R is just the radius of the Earth. I think it's like 6.37 times 10 to the 6 meters. Can't remember. So we can just factor that out. It's not a variable. And I'll just keep it as multiplied by 1 over x squared. These two are the same. You should be able to recognize that. And we have dx. Now what I'm just going to do is I'm just going to integrate both sides. But one of the most important things in these types of questions is the plus c. Because we're not starting, when x equals 0, v is not equal to 0. We're going to have some sort of initial condition, which is our plus c. But one thing we can do to avoid that plus c, when you do a lot of the time without even recognizing it, is by keeping it using a definite integral. We establish limits to this question, and that would avoid having to find plus c, then apply boundary conditions, which I just find a lot longer. So we know that when it's at a height r/4 above the surface of the Earth, the total displacement from the center of the Earth, which is where our initial point of reference is, our frame of reference, one can say, is 5r/4. So I'm just going to rewrite that. So let's say this distance over here is r/4. This is r. So the total distance would be r plus r/4, which is equal to 5r/4. And when it's at a distance of 5r/4 from the center of the Earth, the speed is square root gr/2. So let's say over here, square root gr/2, and the displacement at that point is 5r/4. And so we want to find the displacement at the greatest distance. And as I said initially, when we think about is like a projectile motion, what it means to be at the greatest distance, v is equal to 0. And we just want to find x, basically. We can just let that, the point at which the speed is 0, so the greatest distance, equal x. So now it's practically just basic. We just solved the ordinary differential equation. So we've got, if I just do it in a different color, I'll just do it in red, v squared over 2, with our boundary conditions of root gr/2 and 0 is equal to negative gr squared, negative 1 over x, 5r/4 x. Well, negative 1 over x is just the integral of 1 over x squared. You'll see it a lot if you do engineering or physics. It's basically a very recurring theme in nature, because radioactivity, it's an inverse square law. Radioactivity follows inverse square law. Electrostatic charges, what else? Light. It's a lot in astrophysics as well. Everything practically is inverse square law. It's beautiful. So now if I apply these boundary conditions, we know that that's a bit thick, gr/2/2, which is gr/4, minus 0, it's equal to I can actually cancel out these negatives. It makes life a bit easier. gr squared 1 over 5r/4 minus 1 over x. Some bit of hyperspace. Let's just keep on working with this for now. Cancel out an r, cancel out a g. So we've got a quarter is equal to r 4 over 5r minus 1 over x. So now if I expand the brackets, I'm just going to do it from the side over here. I can say that 1 over 4 is equal to 4 over 5 minus 1 over x. Take 1 over x to this side is equal to 4 over 5. Take away a quarter. I don't have a calculator, so I'm just going to make a common denominator of 20. So 1 over x. Oops, sorry. There's also meant to be an r over here, sorry. It's r over x. Because you're multiplying r by 1 over x. Yeah, my bad. So r over x is equal to 16 minus 5 over 20, which is 11 over 20. Just cross multiply a little bit. You get 20r is equal to 11x. we want to find x as a function of the radius. That'd be, so we just want x is some function of r. Therefore, x is equal to 20r over 11. Let me just rewrite that to make it a bit more clear. And that's your final answer. Thank you for watching.